Boston.
I've got a former student, I know a Haas alum who is the Chief Innovation Officer for Santander Bank, which is based in Spain.
Sure.
And he refused to move from the Bay Area. So he's a one-man office in the Bay Area.
I'm very familiar with them. We are, so Smarter HQ, which I'm not going to talk about, I'm not going to show the company, but we do behavioral personalization for mostly retail, but Santander is just one of our new acquisitions. So they're using us to do for personalization on the website and in email.
Okay, well, bricks and mortar.
Yeah, well, for them, we're just doing online, but for many of our other clients, we integrate the online with the offline OMS data to get a customer view of multiple channels of interaction, which is very interesting.
Yeah, there's so much new stuff happening, and as retail fights back with the, measuring consumer behavior.
The thing that's interesting, so even though, yes, I mean, so many retailers are closing stores and doing all that, but in-store still rules the day. I mean, it's not like online transactions are outpacing, the growth is high, but it's still, what, 15% of transactions are online versus in-store.
For me, I think it's about 99%.
I know, I always buy online. I don't like going in store, but I don't like shopping either. So,
right. Yeah.
I just.
Okay. I know. I can't wait. Amazon's got this new thing where they'll deliver before you order. Yeah, which I'm so in favor of that. It saves me the hassle of pushing the one click. It's so cool. I'm all over it. Okay, well, let's get started. I think there's a couple people who are going to straggle in, but I wanted to introduce Dean Abbott, who is the author of this book here, Applied Predictive Analytics, which I highly recommend. It takes data science and converts it into plain English with a whole lot of cool pictures. It overlaps slightly with the book that you have already been reading, but then there's a whole bunch of other new stuff that's not touched on in that book. And he is, you still have Abbott Analytics, right?
Yeah, just for teaching purposes,
okay.
That's a brain, but 120% of my time is I'm the chief data scientist and now CTO of Smarter HQ, which is this, and co-founder, which I did not expect it to go this far. So I was one of those, I met the other co-founder at a conference in San Francisco, had a good idea, marrying up retail and predictive analytics about 8 years ago. And I said, okay, I'll help you out with this and help build out all the data infrastructure. He was doing all the marketing side and the consulting side. But my wife kept saying, Dean, what are you doing with this guy? Do you know him? Do you know anything about him? I'm like, oh, just a cool idea. I think it's going to go somewhere. So finally, we got our first venture round in 2014 from Battery out of Boston. That's when I was all in. So Abbott Analytics kind of went on hiatus for a period of time, though I still use that umbrella for teaching. Things like generally this or Predictive Analytics World is where I was earlier today and yesterday, teaching workshops on model ensembles and methods. So, but one thing I'm really glad you're in good hands with the instruction, because I really enjoyed sitting through your discussion of the algorithms at a high level, very clear. But as much as I'd love to talk about that stuff, which is, it's a blast to talk. I mean, this whole subject area is so much fun for me. I've been doing it for 30 years, and it really has not changed in 30 years, except for there are some new ideas. But the general framework of everything we do is exactly the same as it was 30 years ago, back when I was doing like missile guidance and sonar back in my early days coming out of grad school. Which makes it easy because these techniques can be applied so broadly. But today I want to shift the focus away from the algorithms per se, at least in the beginning. At the end, I'll return to algorithms and talk about how the big data world affects the algorithms. This is a higher level talk for the most part with some deep dives into some technical aspects. But it's just thinking about big data and what big data means for especially enterprise companies now who really have to handle the problems associated with big data. So I'm a fan of old Clint Eastwood movies, like The Good, the Bad, and the Ugly. And to me, big data matches up very well. So there's a good part of big data, there's a bad part, and there's a really ugly part of big data. I want to cover each of those characteristics. So this is the typical kind of word cloud you might see related to big data. And you see all kinds of things, which what I found interesting about this from olap.com is, of course, big data is in the center of it. But some of the other big words, obviously large and synonyms like that, but information and information technology, especially that word information really stuck out to me because that's what we really want out of our big data. The reason why people like the idea of big data is to collect more information to describe behaviors, characteristics, things we want to gain insight from. And so I like this word cloud. I'm not, by the way, if you do, I don't know if you do text mining during this at all. I'm not a fan of word clouds in general. I mean, they're kind of eye candy and fun to look at, but in terms of their true value, I think they're pretty limited. Okay, so here's your typical kind of slide that you'll see on big data. And here it's talking about the 4 V's of big data. So what they usually describe are things like this: the volume of data, how much of it there is. That's what makes big data big, obviously, a lot of it. The variety of data, different kinds of data. And variety of data really means collecting, I'm going to show some examples in a moment, from different sources, different tables, internal data, external data, just trying to grab as much of it as you can and try to integrate it in your database somewhere. The velocity of data, streaming data, how quickly it's coming in. And the big craze now is with Internet of Things and IoT data and sensor data streaming in, just incredible volumes of data coming in. And even from the retail perspective, when you're collecting web data, web browsing behavior, it's a lot of data, especially if you're capturing not just click events, but if you start collecting mouse hover events, location, proximity on the page, everything somebody does on the website, you can capture and try to gain insight into what their intent is, what they're trying to do during their navigation. And then for retail, the holy grail is the in-store experience. Can you monitor, can you understand what people are doing in-store? Can you use beaconing or something to know where people are in the store? I know it's starting to sound kind of creepy if you go too far down that road, but we could talk later about creepiness versus what customers and consumers seem to want, which is a different question. Not everybody wants it, but a lot of people want more personalization. And veracity, I actually usually, if I do this, I actually cross that out. To me, the veracity of the data is not a big data question. We care about the veracity of all data, big or small. What makes big data are the 3 V's, volume, variety, and velocity. And veracity we care about, but that's always the case. So what's the good part of this? And just pausing for a moment, if you've got a question at any point, there's plenty of time to ask any questions. So feel free to ask away. Don't wait till the end. This is not like some formal lecture where I'm just trying to regurgitate a bunch of material and you're supposed to just nod and agree. So go ahead and ask questions or disagree at any point. So the good part about it is, first of all, people care. And this Harvard Business Review article, Tom Davenport and DJ Patil was highlighting this, the data scientist, the sexiest job of the 21st century. And like I tell people who come to some of my courses, if you want to get a salary bump, just change your job title, include data science somewhere, and you're automatically going to get that 10, 15K bump in your salary, so it seems. But it's not different, but it's sexier now. So I was talking with James Taylor, who I don't know if you talk about his stuff, decision management stuff at all here, but he's also at the Predictive Analytics World Conference that I'm speaking at this week. James and I were talking about kind of this big data world that we're living in, and data science in particular, and he thinks data science is heading into that trough of disillusionment, you know, with the Gartner kind of style and the wave of the enlightenment stage and the disillusionment stages and all the stages of that life cycle. I think he's probably right because it's been so overhyped, and so many people I see with data science labels attached to their names, to me, are just, they're DBAs. or they're just programmers. And because they're working with data at some level, they've got data science attached there somewhere. But are they thinking about the data the way data scientists should? And when I say the way data scientists should, I mean trying to understand not just what the data is and how it's stored, but what it means and what it means contextually for the organization. So that takes a little more thought. And so I usually describe this as the Freakonomics mindset. So if you've ever read the book Freakonomics, that doesn't mention data mining or analytics anywhere, but it's a data-centric book. And the whole premise of the book is if you peel back the onion of data, you can understand more of the process behind how the data was collected and what it means. Like our sumo wrestling match is fixed. And he discovered, yes, they must be fixed because the patterns that you see just could not happen by chance. So that, I find those interesting. So, oh, by the way, DJ Patil was also the first chief data scientist of our country. So under the Obama administration, he had that role. So there we go, data science, even reaching the pinnacles of our public service. So big data. Here are a couple charts to try to give some motivation of the trends with big data, how many zettabytes of data we're collecting, the big data market, $122 billion by 2025, growing rapidly. Now I know, big data is the easiest term to knock because we've all done the jokes about how ridiculous the big data craze is. Yeah, what's going to come after big data? Is it going to be bigger data or humongous data or whatever? Because it is kind of silly from that standpoint. But the good thing about it is when you say big data to decision makers, to the director, VP, and C-suite level, there's some intuition about what it is and what it means for the organization. So I hear this a lot in courses I teach that practitioners will come and they'll say, I'm here because my boss says we need to do big data. And so I've got to learn about what that means. And so, which is perfectly fine, but it's not an entity. It's not that you buy like a piece of software. It's a lot more than that. So that's why it can be knocked so much. But I've come to embrace the term big data. Just it's fine. I'm fine with it as long as what it means is we're just trying to collect more and more information and data to help our decisions. So the global big data market, this is just looking at big data hardware, software, professional services. Once again, it's just growing extraordinarily quickly. And it's being picked up by all the big news outlets like Forbes. So what does it mean in terms of the data itself? And when I think about the big data world, a lot of what big data means is not just one big chunk of data. It means lots, to the big data chart, lots of sources of data. So for my company, it means a lot of tables. Here's a bunch of tables in a database, all these schemas that you're trying to integrate together. So it could be in your Oracle or DB2 or MySQL or SQL Server or whatever database you're using. There could be hundreds of tables that have interesting information in them that nobody has ever integrated together. If you can figure out how to join them together, you can augment the stories you tell with the data. CRM and back office systems, CRM systems, OMS systems with offline data can be integrated in. You can just grab flat files, anything you collect. So I've worked with some organizations and they get a flat file feed of weather data every day and they just dump it out and you can suck it in, integrate it in with the rest of your data to get some insights into how weather affects your processes. And IoT data, streaming data that comes from the cloud, which is why it's got that kind of cloud symbol. We need to grab all these and integrate them. So this is a picture here from a software tool called NIME that I use a lot for teaching, and I use it operationally sometimes too. That's just showing these ETL processes. You've got different data sources, you're doing database joins or joining on some key and trying to build a single modeling table. Because in the end, any kind of predictive analytics we do, no matter how big or small the data is, has to be in essentially a single table or an Excel spreadsheet. Sometimes I call it loadable in the spreadsheet. So if you can stick it into one spreadsheet, then it's suitable for modeling, which means that all of that data we have up here, all these tables, all these relational entities have to be transformed in a way to flatten them out, which can be an incredible task unto itself. Yes?
So one of the challenges that a data science person would run into is like, what do all those different sets of data mean, right? When you're trying to join all these different data sets, even though they may like mean the same thing. So in terms of like practical application of this, when you go into a company, how do you analyze what do those rows and columns mean on the data, and then how do you bring it all together across so many different channels and kind of create that one table that you can kind of look at?
Yes, you have to ask a lot of questions. And there's a translation process that you have to go through. So actually, I was talking about this topic with James Taylor this morning at the conference, because that's what he does a lot of, working with decision makers. And he said the problem is, and I've experienced the exact same thing, the problem is that decision makers cannot articulate, or subject matter experts cannot articulate what they really want. So they'll say, I want to build this new process, I want to do better customer acquisition. So I think we're going to need to pull in this data because we want to identify, I don't know what it is, their social networks and their web browsing behavior, integrate it and make these decisions. And it turns out that oftentimes when you do exactly that, because a data scientist will hear that, and they'll go out and they'll say, okay, I'll do it. And they go and they find the data, they build it, they try to integrate it all together and say, here it is. And it turns out that it's nothing like what the decision maker really wanted. They couldn't even articulate exactly what they wanted. I had this experience with the IRS when I was building models for them. So I'd talk to a subject matter expert and say, okay, we want to build risk models to identify which tax returns are potentially non-compliant so that we could do workload management, send the higher risk tax returns out to the field to be worked by an auditor. So he said, well, I don't know exactly what to look for. Look, I'm not a tax expert. I'm just a data science kind of guy. So what should I look at? So the first time I did this exercise about 10 years ago with them, they said, well, we look at this and this, and they showed all the line items they looked at, and I'm looking at the line items that he's saying, and I'm looking at the data that the IRS transcribed at that time, and I'm seeing that they're not matching up at all. And so I said, okay, which of these, this is the data that we have available to us right now, which of these would you use? And he said, oh, I wouldn't use any of those. So I don't know why the IRS transcribed those particular line items in the tax returns, but they did. Maybe at some point they were valuable, and at some point they were the differentiators, but they no longer were. And so this guy didn't, so he helped me with that. When the IRS started with mandatory e-file, now you had the whole universe available. So I go back to him, what do you do? Now we've got all these. This is the interesting thing. He described some of the things he would look at. So he said, I look at like line 23 of the top form, and then I look at the M3 return and the ratio of this line item to the M3 return line item 7A. If that's more than 3, then there's something out of whack. That's one of the risk factors. Okay, so I said, great, let me build that. So I built that particular feature, that ratio feature, and I thresholded it the way he said I thresholded it, and I found all these results. And some of them looked really weird. Sometimes the ratio was like 1,000,000. I said, I'm seeing some weird things in the data. Can you help me understand what they are? And he looked at it, he says, oh, well, the denominator is too small. I mean, I would ignore that. Well, I didn't know that. The algorithms have, I'm moderately smart guy. The algorithms have no common sense. The algorithms only do exactly what we tell them to do with the data. So they would have no idea that these are irrelevant things. So we've got to build into the process all the things that could matter for the ultimate decision. So that's a long-winded story to say that part of the process is understanding, trying to tap into the subject matter experts and understand what they see in the data, but they will never articulate it completely. You've got to ask a lot of questions to dig deeper to understand what it all means. So, and that's what James was describing to me this morning too. How do you get at that it takes a lot of good questions where you're trying to get them to expound on, not to solve the problem, but to expound on the ideas. So a lot of times when he goes into a client site, he said they send him to the IT department because they think that's where he wants to live. He goes, no, no, I want to talk to the decision makers. I want to talk to the marketing department of the business folks to understand qualitatively what they're trying to accomplish with the data. And then the data scientists can do that translation between what the business sees and what is in the data, talk to the IT people, what's in the data, and try to marry the two up so that the data is represented in a way that makes sense. So when Angel Morales, my co-founder, and I first started down this path with Smarter HQ, we started building out all the data that we thought we'd need, and we argued for days, and I do mean days, over the data, because we're trying to figure out conceptually how to represent the data. What should a record represent in our data? Should it be a customer? Should it be a customer day? Should it be a customer hour? You know, what's the representation? And it bothered him that the columns in the data were not concise and compact. A relational database will have lots of different tables representing different ideas, and then you join them to build out your full table. But when you do that, you may end up with duplicates, right? So you may have a record. If you're looking at the customer day level and you're including demographics, that same demographic typically will apply record after record after record after record. It's not an efficient way to represent the data, but it's an informative way to do it. Because if the unit of analysis is a customer day, we want in the columns of the data every shred of information we can collect to describe what that customer looks like on that day. All their history, their characteristics, their demographics, everything we can collect on them so that we can have the most complete representation of that customer day, which will change the next day, which will change the day after that. So getting that representation, what a row means and what the column information is, can take quite a bit of time and effort to try to uncover from the decision makers. So I took a long time to explain that, in part because it takes a long time to interview and discuss with business leaders and try to pull that out. Is that scalable? And that was my other question for James. Do you need to be like one of these special breed of people who can do exec speak or SME, subject matter expert speak, and analytics speak in order to integrate these two? And his view is you don't. You can learn how to do this. I think you can, but it's hard. I see more projects fail because of that process isn't done right. So you've got data scientists solving problems exceedingly well that are completely irrelevant, or you've got business domain experts telling data science to solve problems that do not move the needle operationally. They're solving the wrong problem. So that's a big issue. And I'm actually going to get back to that concept in a moment with another, hopefully, amusing story. So, okay, so we integrate all this stuff together into that final table. Again, rows, the unit of analysis. For the IRS, it may be a tax return. It's actually a tax return for a particular tax year is a record in the data. For Smarter HQ, it's typically a customer day. For when I've done invoice fraud, we've looked at an invoice number, so we score every invoice coming in. For credit card transactions, it's a swipe. So you could have multiple swipes for that same card, for the same customer, but you're scoring the individual swipe. So the model should be based upon that level of aggregation, so the decision can be applied to that swipe. So how you lay out the data depends on the problem you're trying to solve. So then, when you get big data, and I don't know if you've talked about any of the statistical aspects of data itself, here is a data set, this donation modeling data set with a bunch of characteristics in the data set, their last gift, the last date, the date of their last gift, some RFM features, recency, frequency, monetary, or they called it here recency, frequency, amount, how frequently they gave, and what amounts they give historically, how many gifts they've given over the lifetime. And here's a simple logistic regression model showing all these data points. If you double the number of records you have, literally double it, look at the p-values which describe how significant these variables are in that logistic regression model, the p-values go down. If you make it 8 times as big, the p-values go down, generally speaking, even more. And I guess they do go down more. Last gift goes from 0.57 down to 0.11. There's no, I guarantee there's no additional information content in these 3 models. The only difference is how many records you have. Now, it's cheating a little bit because these kinds of algorithms are assuming every record is independent. And I don't know if you've talked about IID concepts or anything like that, but the assumption with these algorithms is that every record is an independent picture of whatever process you're trying to build models on. And in this case, it wasn't. I just replicated data. But the reality is we don't try to uncover that independence. We just load up a bunch of data and away you go. So there's going to be replicas, there's going to be records that are tied to other records. We're not going to be ascribing to that requirement very strongly, which means the more data we have, the more significant everything looks. So I used to go to conferences with a lot of statisticians, and when I was there, I'd ask them this question. I'd say, so I see what you're doing with linear and logistic regression. If you've got 100 records and you're building models and the p-values really matter, what do you do when you have 1 million records? How do you interpret your p-values? And the answers I got were fascinating because some of them would say, oh, well, instead of 0.05, which you may have heard that before, the 0.05 threshold for significance is like the gold standard among many, that if you're not below the 0.05, then it's not significant and you'll ignore it. Well, they say, well, what I do is I make it like 0.01 or 0.001 or something a lot smaller. And others did other things. But that one in particular was fascinating to me because what they were saying is, I don't believe the p-value. I'm going to choose a different threshold so that some of the variables get cut out. And their real metric was how many variables they'd have in the model, and they're using the p-values to buttress their argument. They weren't using it as the foundation. They were using it as their cover for which ones they chose. So the bigger your data is, the more significant everything becomes from a statistical test perspective. So we can no longer use those p-values the same way statisticians have traditionally used them to make decisions. And so,
It's true for if you increase the number of variables just because out of random chance, some of them will have a good p-value, but it won't be a good.
and we're going to get to that exact point in a moment. The more variables you include, it does other things to your data, which are, now, from that standpoint, it's not the p-value per se, except for what you described as the random chance that something will happen to a line, spurious correlations, and we'll talk about spurious correlations in a moment. You are right. The more variables you include, the more problems you have with that. So one way to view this kind of problem and how we can overcome it is with zip codes. So there are 9, the first digit in the zip code, these are the regions for those first digit, and there are 900 first 3 digits of zip codes in the United States. There's roughly 30,000 residential zip 5s, and zip plus the zip 5 plus 4, the 9-digit zip code, there's about 45 million of them. And that gets down to the household. And then zip plus 5 plus 2, the 11-digit zip code, gets to a specific like suite or part of that building. Lots of data. And so from a demographic perspective, you know, that's what a lot of people will want to do. They'll say, what zip code does someone reside in when we're building our models? Now, they really don't care about the zip code. Nobody really cares about the zip code. What we care about is what does that zip code represent? So when we're saying that this zip code is a better zip code to target, I used to build models for the New York Times. When I build models for them, one of the things we're trying to do is score every zip code, so when they bought lists from The Economist or The New Yorker or whoever they bought it from, they would buy good lists that would be more likely to respond to, at that point they're trying to do their digital channel acquisition. They wanted to get a good chunk of people to mail to who will subscribe to their online services. So, but they didn't care about the zip code. What they cared about what the zip code represented. And demographic data is a good example of doing exactly that. When you get demographic data, you get things like home values, income, you get racial characteristics, economic characteristics of zip codes. And that's the part that's interesting, because you could be in Santa Monica or in King County in New York, and you could have very similar characteristics, and even though they're geographically very far away, they behave in very similar ways. And that's all we care about from a predictive modeling standpoint. So it looks like big data, but it can be made smaller because of this overlay on top of the data. So we want to feed the algorithm beast, though, because the more data we feed in to the algorithms, we hope more good things will come out of it. But alas, there are plenty of problems with this process. And just because we've got big data, another Harvard Business Review article, it's not enough. We need to be able to do something useful with big data, and big data can fool us. So back to your question about how you translate business objectives into data science or machine learning objectives. There's a fascinating debate at a Strata conference. This is from 2012. And I fully admit, I didn't go to this conference, but I was interested in it, so I looked online to get more information about it. And the only free thing they had online was this debate, which turned out to be great because it was a very interesting debate. It was an Oxford-style debate on whom should your first hire be? Who should you hire first? Should it be a data scientist or a domain expert? Okay, now this is a Strata conference, so you know how this ended, but it's a really interesting question. So data scientists or domain experts, they're going back and forth describing all the reasons why you really should hire data scientists. And there's a perception out there that I don't agree with, that the data will completely tell the story. If you just collect enough data, the data scientist can uncover it. The data scientist doesn't need to be directed. You just do discovery of the data, and the data tells the stories. And in fact, Claudia Perlich, who is she's CEO at Data Distilleries, phenomenal researcher, very well accomplished, and she's won multiple KDD Cup competitions, one of these data competitions before Kaggle came along. And she was there. And so they came up to her and said, so Claudia, you've won all these competitions. What do you think about this? And she said, I assure you that I don't know anything about breast cancer. And she won the breast cancer KDD Cup competition and a couple others. So I can assure you I don't know anything about any of those. But with good Google searching and common sense and strong machine learning capabilities, you can solve these problems. So at that point, I screamed at the screen something. It was clean, but I screamed at the screen and complained. And I told Claudia later what I said, and she agreed with me. Because I was telling this story at another conference that she's speaking at. I said, Claudia, I'm going to reference you, and I want to make sure you're okay with it before you say anything. So I told her what I was going to say, and she says, oh, no, I agree with you. So this is what I said. When you set up competitions like this, what do they give you for the competition? They give you the problem definition, okay? They give you the target variable. They give you the data. They give you the metric by which you're going to judge if a model is good or not. And I can tell you, once you do that, you've solved 80, 90% of the problem. Because once you get there, once you know what you're looking for, the machine learning part, that's the easy part. That's the fun part too, but that's the easiest part of the problem. Defining the problem is critical. And in order to define the problem, where I would disagree with them, you first and foremost need to have that domain expert who understands what you're trying to do with the data. What is the business objective for any kind of analytics at all? Are you trying to do customer acquisition? What kinds of customers are you trying to acquire? What are you going to do once you acquire those customers? Because that will inform the kinds of models you build and what you want the models to do for you. And so typically with the startups, you're starting with somebody who knows something about the industry. And if you already have a domain expert as the CEO or something, then hiring a data scientist is a good idea. With Smarter HQ, Angel was the domain expert. He was a consultant in retail for years. I was the data science guy. We talked, and I said we wrestled, and he would draw pictures explaining his ideas, and I had no idea what they meant, so I'd ask him to explain them. And he would try to, and I wouldn't understand. Then I would try to explain it again, and he wouldn't understand what I was saying. And we finally wrestled enough till we solved it. Our first hire after that was a database guy. And so it was the three of us for a while. And that, to me, and I don't know if I put the slide in this deck. I didn't. I usually put a slide at this point, the three-legged stool of successful analytics. So then that's the three-legged stool. To me, to be successful, you need to understand the problem you're trying to solve, the domain expert. You need to have data. You need to have somebody who knows how to get the data, how to transform the data, how to make the data available. And you need the data science piece, someone who knows what to do with the data once you have it. And part of it too, you want all three of those people in the room when you're defining the problem, because for the reasons I was mentioning before, the data scientists will start asking questions of the domain expert that the domain expert wasn't thinking, because that person may not understand what the data science algorithms can do, and especially what they can't do. Just because you throw out this idea, hey, I'm going to build churn models. Great. Oh, I'll give you another example. I was building models for Revenue Canada up in Ottawa, their IRS. And they wanted to uncover a new process for how they treated debt. So if somebody owed money to the CRA, the Revenue Canada, what should they do? So I asked, okay, so what's your process now? Well, they had kind of a set of rules. So if you're late filing a tax return and you owe money, it depends on how much you owe and if you've done this before and all these things to be triaged to either get a soft letter or a hard letter or any one of these or a visit from an agent. So that's all well and good. So then they said, we want to optimize that. Okay, great. Do you ever have, for the same person that you're going to treat, do you ever give them a soft letter sometimes, give them a hard letter sometimes to see how they respond? Oh no, we do the same process every time. I said, if you're doing the same process every time, this pattern always gets this treatment, there's nothing I can do for you because there's no variety. I don't know, I can't uncover which characteristics of a person's historic behavior will be most served or best served by a different treatment unless there's some variety in the data. They'd have to reconstruct the data. Now that was a misunderstanding on their domain experts' part of what analytics really does. If you do the same thing over and over again, there's no way you can uncover the differences in the patterns of behavior. And big data, getting to the question we had a moment ago about too many fields, you can be fooled by big data. The more fields you have, the more likely it is you can be fooled by randomness. Or David Hand talks about the uncertainty principle, coincidences that occur, rare events that occur much more often than you would expect naturally. So we have to be careful, the more data we collect, that we don't get fooled by the data. John Elder at Predictive Analytics World described a solution to this, which we don't have time to get into, but there are things you can do to guard against this idea of hypothesis testing generating lots and lots of models. So there's a concept in predictive modeling where what we want to do is load up tons of data and then just try all kinds of things. Build thousands, maybe millions of models, compete them out, have the winner emerge victorious from all this competition. The problem is the more comparisons to your point before, the more comparisons you make, the more likely it is you'll uncover something just by chance that happens to line up. And with smaller data, it happens much more often, but you'll see these spurious correlations at one of my favorite websites. You can go there and discover these yourself. But things like murders by steam is highly correlated with, the age of Miss America is highly correlated with murders by steam, hot vapors, and hot objects. And here's the data, you can see how closely they track. Or people who drowned after falling out of a fishing boat is highly correlated with the marriage rate in Kentucky. And of course, these are just whimsical examples, but the more data you collect, the more likely it is you're going to uncover these kinds of random effects. And you can put in your own characteristics, the number of people killed by dogs, and the runs scored by World Series, by a losing team. There's all kinds of things like this. So there's a peril that comes with multiple comparisons. So I looked at this. There's a researcher at UMass named David Jensen, who I love because he's understandable. He's one of these academics who writes in English, which is tremendously valuable. So he was looking at the problem of multiple comparisons, multiple models built with the same objective. And if you do enough of these comparisons, you can uncover these spurious correlations. So if we're looking at the probability that one person, like flipping a coin, these are like coin flip ideas, but with multiple people, the likelihood goes up and up and up and up the more people you interview or you ask for an answer. So if we have, another way to think of it is if we roll dice or if we have 100 continuous variables and we're looking at the age in this PVA data set that was mentioned before, this marketing database, look at the age between 21 and 97 and compare it to a random number. And if we have 100 of these random numbers, eventually you'll start seeing some correlation between them, just the random draws over and over again. Eventually you're going to find a random draw that is correlated with actual data in your database. And the p-values, again, get smaller and smaller and smaller. So I'm not going to go through this in any detail. The concept, though, is this. The more data we collect, especially if that data is unrelated to what we're trying to model, we're just grabbing anything possible, the more data we collect, the more likely it is eventually we're going to hit on something which is correlated, which means we've got to be careful as modelers. And how are we careful about that? Usually it means by doing multiple tests. So we typically do, and I don't know if you've talked about sampling at all, and training and testing and validation. You're talking about sampling tomorrow. So when you talk about sampling tomorrow, you'll get at one of the main ways data scientists handle this with partitioning the data into training and testing subsets or other sampling strategies like bootstrap sampling or cross-validation. Okay, let me get to more of the ugly part of predictive modeling. Big data can cause big, big problems. So if you have 250 rows in your data set and you've got 100 columns and these are all floating point numbers, that will, you'll need about 0.2 uncompressed, you'll need about 200 megabytes to store it. If you have 1,000 columns, so you start measuring more things, you bring in more data sources, so you've got wider and wider data. 10 times as much data, you've got 10 times the size that you need. Of course, if you've got 1,000,000 rows, now you've got 4 times that size. So the more rows you collect, the more columns you collect, the more data you need, the more data you have, and the more RAM you need. So all of these algorithms we talk about, that you're going to talk about here, whether it's k-means clustering or decision trees or neural networks or regression models or naive Bayes, the algorithms typically all work the same way. They load the data into RAM, and then they operate out of memory, local memory. Why? Because it's a lot faster. Once the death knell for any algorithm is swapping data from RAM to your hard drive, virtual disk, to try to pull it, because that's a slow process. So typically what predictive modelers do with that is say, okay, I know I've only got 16 gig of RAM and I've got this big problem to solve. Let me make sure I trim it down enough so that it fits into RAM so I can solve the problem in a reasonable amount of time. That's not a constraint. Yeah, now we get up to 10 million records, or you've got 10 million records and 10,000 columns. Now you've got close to a terabyte of data, which is outstripping RAM in almost any machine, local machine you'd have. And from SmarterHQ's perspective, when we're doing online behavioral data and offline customer data and integrating it all together and building all these measures and metrics, we have the same problem. It's a lot of data. And the data for one of our clients, not even our biggest one, it's roughly about 1.5 terabytes uncompressed. Compressed, it's about a terabyte of data that we use, and we've got to make actionable decisions in real time from that data size. So we're not going to be doing that from my Mac laptop in the back. We need, obviously, more horsepower under the hood. And it's because we're collecting data from lots and lots of different data sources. I'm going to go back here and show one other thing. This is important too, because all these measures in the data, all these columns we build, let me go back to describe what I was mentioning a moment ago. I talked about rows and columns in the data. A row, the unit of analysis, a customer, an invoice, a tax return, and all the descriptors of that unit of analysis that we collect in the data. Those are the main things we're looking at in the data. But something we learn from experience as predictive modelers is those main effect ideas are good, but usually the most valuable piece of information we get, the most valuable ways we can predict the outcome is by combining those columns. It's not by adding them together, by combining them. And that combination can come in many forms. It can be multiplicative. It can be, which is the same thing as an interaction effect. That's why people love decision trees. Decision trees are interaction detectors. In fact, the first decision tree, the AID decision tree, the AID algorithm, automatic interaction detection algorithm that turned into CHAID, the chi-square automatic interaction detection decision tree, which is used as a chi-square statistic. But that is finding interactions. Now, you think of a decision tree, you split here and you split here. So the rule says if this is true and this is true, then some outcome is true. That and is an interaction. Logistic regression cannot find that on its own. It can't, because it doesn't have the horsepower, it doesn't have the math behind it to find that. The only tool in the logistic regression toolbox is linear combination, additive combination of variables. So you've got all your variables, and you take some weight times this, plus some weight times this variable, some weight times this variable, and that's it. So that means if we want interactions to flow into something like a logistic regression model, we've got to do something different. And here are the number of two-way combinations we have possible. So one of the great features, new versions, derived attributes we can create that makes our big data even bigger is two-way interactions, adding these interactions to your data. And so if you started with 5 variables and you want to find all the pairwise interactions of those 5 variables, there are 10 two-way combinations. If you've got 100 variables, there are 49 or 50 interactions. Now, if you've got 5 or 10 interactions, you might do that yourself. You just kind of build them out, build out new columns. Once you get to 100, 500, if you've got 1,000 variables and you've got to build all these interactions, even the most dedicated data scientist is not going to sit there and manually build 499,000 interactions. We need a way to handle this and scale it up. The reason why we care is because some algorithms really need this. Naive Bayes needs interactions. It can find combinations, but naive Bayes does not find interactions. Logistic regression does not find interactions. K-means clustering cannot find interactions. Linear regression cannot find interactions. Principal component analysis cannot find interactions on its own. We've got to help these algorithms out. Neural networks can. Decision trees can find these kinds of interactions. So we have to build them for some algorithms, not so much for others. So all of these things that we've been talking about, whether the creating features, and all of the data preparation we have to do that I'm not going to get into here, big data makes it more painful. And that's the bad part. It takes longer. It's more difficult. So we need a better idea. How are we going to handle bigger data, and how are we going to handle all the additional computation we need? Now, Terence Tao is super smart. Like, I think it's supposedly the highest IQ on the planet, whatever, 230, which is pretty smart. Big data, though, is not smart. As much as people want to say big data is smart, big data is just big. No common sense, and no common sense, it's even worse than that, because the algorithms that consume big data, not only do they not know what it really means, they have no way of doing the things that regular mortals like us, regular human beings, do all the time. Because remember the IRS story? What he said was, oh, I never look at that when it's 1 million, or when the denominator is less than $1 million, I never look at that ratio. Well, he knows that. The algorithm certainly doesn't know that. The algorithm does exactly what it's told to do. You build a feature, it'll use it. If we know that we want to ignore subpopulations, we don't know that. And if, let's say we have a field in our data that's like a state field, and there's one state that's called 1A in that data set. And we know, or we would guess, oh, it must be a typo and it's really Iowa. But the algorithm doesn't know that. To the algorithm, oh, 1A. How about that? There's a new state. That's pretty cool. And there's one example of it in my data. So it's a rare event. Maybe I really need to pay attention. You know, it's not thinking rationally about it. Well, no, I should put it a different way. It's thinking rationally about it, but it's not thinking from a common sense perspective because our experience extends beyond the data. We know other things outside of the data. The algorithms only know what's in the data. That's it. Nothing more, nothing less. So it's our job as data scientists to make sure we're communicating as much information as possible in the data in a transparent way so that the algorithms can understand what we want them to understand about the patterns. So we need to be careful and we only need to use what we need. So one way we can attach this, the big data problem, lots of rows, lots of columns. One way we can handle this is instead of trying to build the one monster model to solve all the problems, we can consider breaking it down into pieces. So just a simple kind of example, if we're building models to identify zip codes that are good for the New York Times, we could try to build a model that characterizes the entire country and all the characteristics of the country in one model. But another approach could be to break it down into regions and build specific models for each region, maybe even specific models for each state if there are significant differences that we find between the states. Why might we do that? It depends on the algorithm you use, but there's some algorithms, like let's say linear regression or logistic regression. What's the tool in their toolbox? Logistic regression is a linear separator. So if your data aligns nicely and you've got this side of the line and this side of the line, or in multidimensional space, it's a plane, this side of the plane and this side of the plane. If your data aligns like that, that's great. But what if your data is not so linear and there are pieces of it, it's a piecewise linear process? Then chopping up the problem into subgroups can help that particular algorithm solve the problem more effectively. So sometimes chopping up your problem is helpful. But if you want to use it all, which we typically want to do, let me describe another thing. This is more the punchline of the entire talk today. How do we scale up environments? And one way is using cloud infrastructure. So this was, as of last year, the leaders, according to Gartner, in their Magic Quadrant, in cloud computing were Amazon Web Services and Microsoft, especially Azure. And of course, Google is up there, and there's a bunch of other companies that are involved with this as well. By the way, everybody's doing this now. You talk to IBM, their big initiatives are moving to the cloud. Talk to Oracle, their big initiatives are moving to the cloud. Everybody's moving to the cloud, which the cloud isn't mysterious. It's just somebody else's computer, right? So, but it's somebody else's computer with infrastructure that goes beyond what we want to spend time managing. So we're letting somebody else manage the infrastructure and use their computing services, pay more for it so that we don't have to do it. That's the whole game. So my company, SmartHQ, we live in the AWS world, and we do it largely because we have a very lean DevOps staff. We have a very lean staff of developers. We don't want to spend time managing infrastructure. So we lean on Amazon to manage all that infrastructure. And so with the cloud computing infrastructure, you'll see something like Amazon, where they've got S3. S3 is their data lake. And again, data lakes, they get lots of buzz, but it's just a dumping ground for data. That's all. You can just dump stuff there, and they built incredible efficiencies so that you can dump data in S3 and it can feed these other databases that they support. So the Redshift is the Amazon Big Data database, the columnar data store, which means it handles wide data more efficiently than your typical Oracle transactional database, a MySQL database, SQL Server database. It handles wide data better. So the other databases out there that are similar to Redshift are like with Vertica is a company that is acquired by HP that does wide data. Netezza is a big data, wide data store company that was bought by IBM, and there are a bunch of these solutions out there in the space. So at Smarter HQ, we use S3, we use Redshift. EC2 are just servers. Microsoft has their Azure machine learning, where they want you to dump data in, use their machine learning services to automatically build models for you, and they charge you per model interrogation, per prediction, like some fraction of a penny. So it's pretty cheap if you've just got a few models, and they manage the machine learning infrastructure for you. So you can build logistic decision trees, you can build a bunch of different models, you can build deep learning models using their ML Studio, and it's very easy, very cool. And the best part about it is, just like on the Amazon side, it scales. So if you've got big data, if you've got wide data, you can think about using these kinds of services to scale up at a level you can't with your own individual laptop, your own internal architecture and infrastructure.
So how is the availability of that kind of things like ML Studio affected the hiring strategy for companies that are going to be heavily invested in data science?
The biggest hiring thing I see, I mean, Hadoop, so when I think about the data science world in general, what defines data science? And then I'll answer that question more directly. So I'll do an end round first. The big difference to me between the data science community and like the predictive analytics community or the business analytics community is the go-to technologies in data science are R, Python, SQL, Hadoop, Spark, these kinds of languages and infrastructure. So especially the Hadoop side really captured the imagination of the data science community. And so lots of companies were pouring tremendous resources into Hadoop. And so when I say Hadoop, what I mean is especially this MapReduce idea where you parallelize processes by splitting out that data to multiple nodes, have them operate on that data, and then stitch it all back together. And so the speed and the efficiency comes from how wide you can push all that stuff out and how efficiently you can do it. The problem is it was tremendously difficult from a programming standpoint to get the data right. And so there are some great success stories and some huge crash and burn stories of Hadoop, where, and I've spoken with companies who spent millions of dollars building out Hadoop clusters, let's set the data scientists loose, and what they had at the end of the day was a really cool solution that they're trying to figure out, what are we going to do with this now? They talked to the business stakeholders, and they said, well, we've moved on from that. It took a year to build. Now we're past that. Now we want to do something else. Oh, well, we're going to have to rework everything we did in our Hadoop infrastructure to satisfy that need. So what does it mean in terms of skill sets? Data scientists are the companies often want data scientists to have those kind of skill sets. What I hear the most often is R, Python, SQL, and then there's Hadoop is close number 4. And just so you could do these kind of things. Now, with machine learning in Azure, Microsoft brought Revolution R, and so they're making a heavy investment on the R side of the fence. And so scaling R up to the enterprise has been a major initiative of Microsoft with some success. AWS, Amazon, they are more in the Python camp. So they're trying to make Redshift and their infrastructure Python friendly. So I don't know where that's going to land. They both obviously are flexible enough to be able to incorporate both, but that's just a general flavor I'm seeing with those two environments. And AWS, I mentioned I don't know if I've mentioned this yet, EMR, Elastic MapReduce, that's their Hadoop cluster, their style of doing that. And Azure's got their own MapReduce cluster as well. And Google has their own BigQuery storage, BigQuery engine. I don't know much about the Google process at all. I've never even touched it. But they're definitely up and coming. And of course, with the Apache side that they're pushing in Spark is probably the fastest growing of the languages that people are using, approaches people are using for big data analytics. in my company, we're starting to look at Spark for handling the predictive modeling pieces as well. I'm not sure if we're going to do it or not, but it certainly captured our attention. And then you've got some of the classic companies that have been in this world for a long time. Teradata, of course, was the original big data company supplying hardware and infrastructure for the biggest industries, like the airline industry and all the reservation services as one example. They're also, when you see this, moving to the private cloud as opposed to the public cloud. So having a cloud infrastructure for companies that are not part of their public and shareable infrastructure is something that Teradata has been launching into because they see the value of cloud computing as well. So why does that matter for us as predictive modelers? So I want to get into this a little bit. So I'm glad you talked about k-means clustering. You've talked about other algorithms because part of the problem that we encounter with something like k-means clustering is related to data size. The bigger the data is, the more algorithms like k-means clustering fail. So let me give you some specific examples here, the number of inputs and the number of clusters. How do you find the right number of clusters? Now you're describing ways you can do that, and there's no real gold standard in how to define the number of clusters, but people may try, 5 or 10 or 50 or 100 and iterate through this process. And that's perfectly fine. But it takes time to do that, and it takes infrastructure to do that. So one of the first use cases for the parallelized architectures I was seeing out there with some of these big data companies, and this is even 10 years ago, there was a company called Pervasive that was bought by Actian. It's a big data, high throughput engine. They were showing examples of using the Netflix prize data, which is pretty big, and running it through k-means clustering with their engine and building anywhere from 10 to 50 to 100 clusters and doing it in seconds on millions of records. So it's really cool. And what I told them, I said, well, of course you use k-means clustering because that's like the simplest algorithm to blow out and parallelize because you do identical processing over and over again. So you could try different numbers of clusters and build this out very efficiently. Of course, the more I thought about that, I said, well, then of course you should do it. And that's one use case for k-means clustering is to use a parallel infrastructure because it's so fast to do that way, which then does something that's particularly important for us as data scientists. It changes the way we think about the problem. So let's think about the number of inputs, for example. You start with 1,000 inputs. And let's say you do all the right things. You normalize the data, you pre-process the data so that all your data is good and ready to go. But you've got 1,000 inputs. Are you going to throw 1,000 inputs into the clustering model? The answer is probably not, because that's 1,000-dimensional space, huge space, and the amount of empty space in a 1,000-dimensional space is enormous. Do you have enough records to fill that? Maybe, maybe not. And k-means really isn't designed for that high dimensionality. And moreover, when you deploy your model, do you want a 1,000-dimensional space model? Do you want every time you get a prediction of which cluster you belong in, it's got to interrogate 1,000 variables to do that? Most clustering solutions that I've seen, people like to land in the dozens to most maybe 100 inputs to your cluster model. And so of these thousands, what should you do? So historically, what people have done is because it's such a big data problem, they say, okay, we've got to whittle down the 1,000 to something small, to like a few dozen. Well, how do you do that? Well, ask the domain expert, which ones do you want in the model? So that's one way to do it, to whittle it down. Another way to do it is to try to find which variables co-occur enough that they could be good candidates for a clustering model. So you could build some numeric procedures to do a quick and dirty variable selection. What I'm arguing here is with big data, you don't have to worry about that. With big data infrastructure, I should say. Because what you can do is try a bunch of them. So you've got your parallel environment. You've got an EC2 box with 36 cores, and you can build a separate k-means clustering model for each one of these cores in parallel and blast out 30, 50, 100, maybe 1,000 cluster models at a time really fast and iterate through the thousands and thousands of permutations you want to try as you search for the right number of inputs and which inputs are the most important. And that first struck me the very first time I was asked to speak at Netiza's headquarters in Marlborough, Mass. In 2008. And that was my first introduction to this columnar data store, big data box, screaming fast processing even then. And even now, it's incredible how fast it runs. They're expensive boxes. They're like $1 million to get these boxes, but they really are fast. Then again, it's easy to spend $1 million in AWS infrastructure too if you pile on enough services. But anyway, that's a different story. So when I went there and described predictive analytics and k-means clustering, and they went through some examples, I was like, so I was running through these cluster models in seconds. And so if instead of minutes and then manually tweaking something and trying it again, if you can automate this process like your Python script or Netiza script or SQL query and just do 10,000 experiments, blast them out, and in an hour, you've tried thousands, tens of thousands of experiments to arrive at your k-means cluster model. I mean, how cool is that? So it just changes the way you think. You're not compromising as much. You're using the infrastructure you have available to you to blast out more models.
How does that relate to the dangers of randomness?
Absolutely. So whenever you do something like this, whenever you're trying more and more things, you always have to assess the results at the back end. Now, one thing I will say, and I've tried to break algorithms in this way, and so I'm feeling a little more comfortable with this whole concept. The bigger your data gets, the number of records, I mean, not width, the more records you have, the less and less likely it is that you can find these spurious correlations. So all those spurious, one thing you'll notice about all those spurious correlations we looked at were dozens, maybe 100 records. So small data sets, it's really easy to find spurious correlations. If you've got 1 million records, it gets much more difficult to try enough new columns. So I've tried that, take 1 million records, and how many columns do I need before I can find 2 columns correlated at like the 0.8 level or above? And I haven't found that yet. So it gets much more difficult to find 2 things that are really correlated with each other at that level. But it's still possible. So like David Hand's book, Fooled by Randomness, is getting at that idea too. And we always think, you meet somebody somewhere that you haven't seen for 20 years, and you just read their book or something, and they just happen to be right there, right then. And you say, what are the odds of something like that happening? Well, as Hand points out, the odds are actually quite high, because that's just one example that gets exposed of the millions of possible things that could happen that are all one-off events. So our perception of what's random or not is not particularly good. So anyway, so yes, with enough records, with lots and lots of records, it gets much easier to avoid the parallels of multiple comparisons. K-nearest neighbor, which is very closely related to k-means clustering. K-nearest neighbor is doing the same. You can see the same kind of SSC plot that you were looking at a moment ago, which I actually borrowed from the k-means clustering plot because it's the same kind of idea. But k-nearest neighbor, it's the same game. What is the optimum set of inputs, and how many nearest neighbors should we use to optimize that k-nearest neighbor model? K-nearest neighbor, by the way, is a really cool algorithm. I mean, it's super simple and super reliable because, so just to decide, I don't know if you'll talk about this, but neural networks, so we're going to talk about neural networks in a moment, but the neural network bigots out there, and I'll just throw it out like that. So the neural network bigots out there will often say, at least they used to say to me, that neural networks are universal approximators. And what is a universal approximator? It means a neural network can be proven, can be shown to be able to emulate or estimate any real valued function, a continuous function, I think. Maybe there's another constraint there too, but it's at least continuous. In other words, they're super flexible. K-nearest neighbor is also considered a universal approximator. You can approximate any function with the k-nearest neighbor. And all k-nearest neighbor is, as either you've heard already or you will hear, is a lookup table. You got your training data and you're done. There's your k-nearest neighbor model. It's the lookup table. It's what you do with that lookup table that matters. So in this example here, it's the one nearest neighbor problem. So who is your nearest neighbor to this new data point you're trying to classify or estimate the value for? And if you use the one nearest neighbor model, you just take the closest to it. Euclidean distance or Manhattan distance or Mahalanobis distance, whatever one you want to use. This is the three nearest neighbor model where you vote. And so one of the questions you get asked is, what's the optimum number of neighbors to use to classify this data? How do you know that? There's no rule to tell you how many to pick. So you can try lots of them, and you can use a big data infrastructure to do that, as well as finding the optimum set of inputs.
One of the things that's unsatisfying in some ways for people
There are lots of things, yes.
to data science is the huge role of kind of trial and error. I mean, when you're trying to figure out which algorithm works, when you're trying to figure out which knobs you want to tune within each type of algorithm, it's trial and error. When you're trying to figure out what the optimal K is for your nearest neighbor or your clustering algorithm, it's kind of trial and error. And so for folks who have domain expertise, who think, well, I have an intuition about what this ought to look like, it sort of bumps up against this sort of let's try everything and see what works approach that data scientists have. Do you see like kind of a clash there in terms of approaches, or is there a way that the data science can become more like a deductive science and less of an inductive?
And that is the goal. So you've got companies spring up like Data Robot, where the idea is to throw data in, and they do all the data prep and all the modeling, and they spit out a prediction. Or SAP HANA is an approach. SAP bought KXEN, and KXEN was one of these software tools that they use a variant of support vector machines, the statistical learning networks that started in the 70s but diverged, but they're related to SVMs. And the whole premise behind KXEN was the analyst, don't have to do anything. Throw the data in, and it'll do reasonable data prep things, do reasonable tuning, and it generates predictions for you without you having to do much of anything. Watson is the probably preeminent example now. You just throw data in, and it tells you all these insights, right? It tells you the whole story, everything you want to know about the data. I feel conflicted like you're describing, because I don't find it that easy, and there's the rules of thumb are helpful, but they don't tell you exactly what to do. And so for people who want a recipe to do this, this, and this, and this, machine learning, AI, or whatever we want to call data science today, is not there yet. The data robots, I hope they're successful, I hope they do well, but I see so many. Let me give you a simple example of how I don't believe Data Robot can solve problems like this. If you're filling in missing values, you got a bunch of missing values in one of your columns, you've got to fill it in to build your neural network or your regression model or whatever, PCA or whatever you're doing. How do you fill that in? So there are automated ways you can fill in missing values. You can use the mean, you can use the median, or one of my more favorites is you can use a distribution, a random draw of your data to fill it in. And those are all fine. But that depends on what you're doing with it. So if I'm looking at models for a bank, and I want to know what marketing programs to send to them, and I'm looking at their checking account balances, their saving account balances, their money market account balances, their credit card balance, and they do not have a savings account. So that's null, that balance. Do I want to impute a mean of the population? Do I want to impute a distribution? Is that conveying to the algorithm, to the model, what's most relevant, what's most informative about that cell? And I would argue absolutely not. I mean, I don't have a savings account. I'm not an average savings account holder. I'm a zero. The best one, I mean, there's no perfect answer to that, but zero is a better answer than the mean, that's for sure. And so how you impute depends on the problem you're trying to solve and how you're trying to communicate the information you want the algorithms to be aware of to solve that problem. So that's why I don't see a way around that. You have to know something. Now, you could get to the point where you say, well, there are 3 different ways to impute missing values we have available. Pick the one that's most applicable. And I could see that you could limit the choices. But to make it completely automatic just from the data itself, I just don't see how that's really possible unless your data is somehow constrained in just the right way.
Link to that. So, for example, ML Studio with Azure, in what way is it replacing versus making a data scientist more efficient or better at what he does?
It's just faster.
Okay.
The algorithms are no different.
Yeah, but it seems like a lot of the stuff can be automated, like the testing which algorithm you should use.
That's right.
The method behind the algorithm itself, you don't need data scientists for that or domain experts. So which parts of the process do you still need who for? I guess for the...
So to me, you need the analyst. The most important role for the analyst, to me, is still preparing the data. I think the building the models is has the most potential for being fully automated. It's still difficult to fully automate because there are ways algorithms can go wrong that are hard to uncover unless you've got somebody who understands where the algorithms might fail to look at it and say, it's a bad model because this parameter is wrong, or you're building a regression model and you've got some extreme outliers in your data that went undetected or whatever it was. And so you say, okay, I know that's going to bias the model, and those kinds of questions. So, but the data prep part in particular, getting the data in the form that the algorithms need in order to build properly, that's probably which is a little painful because that's my least favorite part of the process. I much prefer building the models and assessing them, and I even prefer talking to the domain, the business stakeholder for a long time about the problem. The data prep part is just not fun for me. For some people it is fun, bless them. I hope I meet all of them and they can work with me and work for me, but that's not the fun part for me.
So what's the fun part for you?
Building the models. That's a blast. Trying to figure out this kind of stuff, like, do all these searches, or like with neural nets, trying to figure out how to make the neural network work better, or something we won't talk about here, but especially building model ensembles, taking lots of predictive models and combining them in some way, and seeing how that performs. That's useful. So for neural networks, the issue is architecture. How many hidden layers do we want, and how many neurons in the hidden layer do we want? There's no rule to govern that. And there's rules of thumb. The more complex the problem is, the more neurons you need. Sometimes you may need extra hidden layers, and if you want to build a deep learning neural network, it's essentially lots of hidden layers with some other stuff along with it, but just much more complex. The problem with neural networks, though, is you've got to pick the architecture, but this is the minimization problem with a neural network. Think of it with linear regression. Linear regression is closed form because the math is easy and you can mathematically get to the bottom of the parabola, the bottom of the bowl, in closed form, which means you just say go and it knows what the answer is right away. It's just the math. Neural networks are so complex and so nonlinear, you don't have that. So what you have is a surface that looks more like this, and your neural network is training and training and training, and then it gets stuck here. And you never know if you've hit the global minimum for a neural network or not, ever. All you can do is say, okay, let me try it again and see what happens. It's kind of like when you're describing with clustering, a lot of it is, unfortunately, cut and try. You try something else, see if it works better. Just one side. I know there's been a lot of side things here, but here's one more side thing. These algorithms, as cool as they are, I was almost at the point of despair with machine learning algorithms maybe 10 years ago, and saying, I'm going to punt all this stuff because you've got to force our problems into this framework. These algorithms, what they're trying to solve for is not what the business is solving for. Linear regression is minimizing squared error. I've not worked on a single fraud detection problem or marketing problem where I cared about minimizing square error. I'm concerned about profit. I'm concerned about how many new customers I'm acquiring, what my churn reduction is. Those are the metrics that the business cares about. So here I am building these models that are using the wrong optimization metric, and I'm hoping that it does a good enough job so that my real optimization metric is satisfied. The problem is, where's the alternative? The alternative is with global optimization problems where you can specify exactly what that metric is, but those are so hard to build and so hard to get to converge, like genetic algorithms and simulated annealing and all these guided global optimization problems. And so I despaired even more with that. I said, okay, I'm back to these, because at least these you can build, and you can build these pretty quickly. Okay, so neural networks. There's all these things we can do with the neural networks, and this is very common, by the way. Most of the good implementations of neural networks will do a lot of this for you. It just takes a while. They'll say build 50 neural networks or 100 neural networks. Different architecture, different neurons per hidden layer, different learning parameters, learning rate, momentum, different error metrics, all these different things you can scramble to make the neural networks build better. I mentioned logistic regression. The interaction effects in particular is something I focus on with every logistic regression model I build. I want to find interactions that will help logistic regression. But as I showed you before, that could be a ton of interactions that I don't have time to build. So I have to find an automated way, blasting it out in my cloud infrastructure to find all these interactions. So with SmarterHQ, when we're building predictive models to predict the probability that someone will purchase within 7 days or 3 days or 15 days, we use logistic regression because it's really fast. But it won't be as accurate as a neural network unless we do something else to it. And one of the things we do is go through a search to find all the good interaction effects. Of the hundreds of variables we have, we've built tens of thousands, hundreds of thousands of interactions using association rules. And we pick out the best of them, feed them into the logistic regression model, and now they work really fast and much more accurately. But that just takes time. I thought I had another slide here. I don't have the other slide. The other slide that I thought I had here that somehow I got rid of was even decision trees. When I first arrived, I was really heartened to hear you describe decision trees and how they're greedy searchers. And that is a problem with decision trees. That unless the first split it makes is a reasonable split, you could get off on a bad path. Even if it is the best you could do, it may not be the best in combination with other variables you have in your data. And so sometimes with decision trees, it's just shuffling the data around, scrambling the data that forces, like bootstrap sampling, to force the tree to think about the data in a different way. Or in the limit, what you can do is the random forest algorithm. And I don't know if you're going to talk about random forest at all, but all random forests, to steal your thunder, is decision trees resampled, bootstrap sampling, and random variable selection at each node. And if you randomize which variables you could split on, you force the trees to do different things. You force the tree to find another way to solve the problem. And so that's something you can do with bigger data. You can try more and more random forest models. You can try more and more of these resampled data in order to find the better decision tree solution or random forest solution. Okay, so in conclusion, the big data causes problems for predictive modeling because of scale and the multiple comparisons. The multiple comparisons is mitigated to some degree just by the size of the data that we could end up using, however. We need to leverage the big data wisely. Now, one thing to keep in mind, just because you have big data doesn't mean you have to use it all, right? So you could have 1 billion records, and if you're building a logistic regression model, I can tell you now you don't need 1 billion records to build a good logistic regression model on 10 input variables. It's a linear model. You don't need that many. It's going to be a lot of duplicate information in there. So don't use it all. Use what you need. But the more data you have, the more clever and creative you can be with how you do these searches and finding these subsets and build them out in that cloud environment in a relatively efficient way. So I think it's like 5 minutes before we're supposed to break. So there's time for questions, comments.
Let me ask you one question. you've been doing this for a long time, and so you've seen the transition from relational databases to what we call data lakes, right? And you know that creates a lot of flexibility, right? So you know most companies, apart from sort of I guess traditional financial institutions and others, are kind of moving towards this data lake architecture. Could you just talk a little bit about kind of why that's happening, and you know what the obvious drawbacks are of the relational database, but then on the flip side, you know what benefits are there for keeping a relational?
Yeah, one of the problems with traditional relational databases is the kinds of data we're pulling in, we want to model, does not fit nicely into a relational database structure. So if you've got, just as one example, if you've, like with social media, if you're capturing text from Twitter feeds, I mean, how do you store that in a relational database? So you can create a blob in a cell of text. You can carve out keywords to text and shove it into columns, but that's really that's not the natural way to store that. So NoSQL databases like Mongo that I'm pointing up there because I was thinking about something that I'll go back to. In Redshift, I mean, in the AWS infrastructure, DynamoDB is a lot like Mongo. These NoSQL style databases can handle those kinds of text features better. Or if I'm looking at an experience a consumer has navigating a website, one person may browse 10 items, another person 2, another person 100. How do you represent that in this table? It's a customer, and you could have 100 products that's possible, or let's say we've got 30,000 products. One way to represent that is here's a customer, and here are 30,000 columns, and we put the number of times they interact with that product in a session. That's just a horribly inefficient way to store that data. So DynamoDB or Mongo, or you can create flexible structures around that, or the data lake idea is you can store this data in JSON format or some other format that's flexible and just have the data there in a more natural state. So that makes it easier to store because it's not naturally a transactional kind of data representation. However, that stated, in the end, if you're using machine learning algorithms, you have to convert it into this kind of form that fits nicely in the transactional database structure. And I don't have a picture here to show that, but it has to fit naturally, like loadable in a spreadsheet. You have to get it there eventually. So the data lake is a nice, convenient, intermediate storage location. But it's not the end location for most, especially if we're doing any kind of predictive modeling. You've got to transform it at some point. And my fear, frankly, of the data lakes is that it'll become like my garage, where you just dump stuff in there because you don't have to organize to dump it in. You just dump it all in and say, I'll get to it later. And it's just a mess. I mean, I know with us, our S3 buckets, I mean, we've got to get control over this because people are dumping things in S3 all over the place, and because it's flexible, it's also a mess. So there's no free lunch. I mean, so it's a flexible intermediate storage. That's the great thing about the data lakes. So it buys you time before you decide what you need to do with it. So you don't have to develop the schemas in advance to store the data. You can work out that infrastructure later, or you can apply that the infrastructure to different solutions. Like you could dump it into an S3 bucket and then consume it in Hadoop. And that's one place. But it could be that it's going to be consumed by Hadoop and Elasticsearch and a whole bunch of different technology pieces, but the data lake is the core of where it starts. So you don't have to first push it into a transactional database unnaturally and then rework it to make it work well in Elasticsearch. So tremendously flexible, but tremendously dangerous, I think.
So you're talking about the universal approximators, right? Is there an intuitive way to look at an algorithm and tell whether it's a universal approximator, or because I didn't find it very intuitive to like look at KNN and say that's a universal.
On K-nearest neighbor, in fact, K-nearest neighbor has such a great history. You can prove And not me. I mean, I used to do math, and I've been so much out of the math-centric loop that I couldn't do this anymore. But k-nearest neighbor can be proved to be, at worst for a classifier, twice the Bayes optimal. So what does that mean? The Bayes classifier is the gold standard for classifiers if all of your data is normally distributed. So just like you think about linear regression models, if you've got normally distributed inputs, or more precisely, the relationship between each input and the target variable is this normal constant variance relationship. K-nearest neighbor, same kind of thing. If all your data is normally distributed, it's exceedingly good. The Bayes classifier, assuming normal distributions, is the best you can possibly do. You wouldn't use any other algorithm. It's too bad that's kind of gone by the wayside. It's got a lot of problems, which is why it's gone by the wayside, and why naive Bayes has taken its place as a quick and dirty way of approximating what a Bayes classifier does. But anyway, so you'll see sometimes in the literature, if you read on k-nearest neighbor, oh, it's at worst twice the Bayes optimal classifier, which you can't say about any of these other algorithms. You can't guarantee accuracy. So can you tell just by looking at them which ones are universal approximators? I don't know of a way of doing it. The neural network approach, I mean, that was one of the big selling points years ago for them. And they tried to map it mathematically into the framework of some well-known theorems in applied mathematics by Kolmogorov to show what kinds of functions you can estimate. And because it can map into that, someone discovered, oh, it can approximate any continuous valued function as a result. So, but that's not true for logistic regression. It's not true for decision trees. It's not true for support vector machines. As good as they are. I mean, and that's not a knock on decision trees at all. I love decision trees. I use them all the time. But you just can't guarantee, you can't prove their accuracy.
All right, well, thank you, Dean.